famous in the last few years. So he comes from a different perspective, and still it's interesting to see how two visions can contribute to the same topic. So Koopman operators again, Alexandre.
Okay, just I need to. Okay, so can you see my screen?
Yes, yes.
And you
your desktop, okay. But not your slides.
Oh, okay. This is always the issue. So you see my desktop, but not the slide.
We
okay.
see a nice rock, a climbing rock.
Ah, yeah, okay.
That's you on the picture?
No, it's not me. No. Okay, and what about this?
No.
Maybe we need to wait. You still cannot see it. Okay. I will try again. Can you see the screen?
No, it's still the climbing rock.
It's annoying. Excuse me.
Before we could see it for a short moment. We saw your slides.
Okay. And now?
No.
Now?
Maybe you can stop and restart the screen sharing.
Yes, it's what I did actually.
Yeah, but you have the option to select, okay, I want to share my screen, I want to share this and that for that program.
Yes, there are different options. Oh, apparently there was a pause. The sharing was in, there was a pause in the sharing. I don't know how I did this. Okay, so sorry for this this delay. It's again another talk about Koopmanism, and I would like even to rename it as Koopmania, because actually it becomes more and more popular, and there are researchers working on this Koopmanism, Koopmania in different fields. And here it's just another application of the use of this Koopmanism in the context of identification. And so just as a caveat, and as Rainer said, I'm more from an applied mathematics background. So here in this talk, I will still try to focus a bit more on theory and less on numerics as usual, because of the kind of conference. And I guess you are more interested in theory, but I apologize in advance if it's not enough theoretical or not enough rigorous, and do not hesitate to ask if there are some details that are missing. This being said, let's start. So the identification problem, what is it? Simply, it's the problem that we have some data points which are generated by dynamical systems. And from these data points, we want to recover the dynamics that generated the dynamical system. So basically, we want to recover an ODE or even a PDE or anything else that generated the data. And the usual way to solve this problem is to consider the dynamical systems through its flow. So we have a set of trajectories starting from initial conditions. So this is a representation in low dimension. So basically it could be finite dimensional, but it will be typically nonlinear because we assume that the dynamics is nonlinear. And instead of this perspective, of course, you guess that we can use this Koopmanism and then consider the, excuse me, the dynamical system through the Koopman operator. And now we will consider a high dimensional operator, typically infinite dimensional, but, excuse me, but now the system, the dynamics will be in some sense linear. And so instead of performing some kind of nonlinear identification, we can hope to do some kind of linear identification. So it's why I propose to do here in this talk. So first I will start with a few preliminaries, but we have already said a lot about Koopman operator in this session. Then I will present a method to identify nonlinear ODEs, actually two different methods. And finally, we will consider the case of nonlinear PDEs, so how we can identify nonlinear PDEs. So let's start with the preliminaries. So here we assume that the data will be first, in a first time, generated by a dynamical system, which is simply an ODE, which is in Rn, defined in Rn, and typically we'll consider that the state evolves in a forward invariant compact set. The vector field is C1, so that we have uniqueness of solution and so on. This ODE will generate a flow that I denote by phi t, and the Koopman semigroup will define it through the composition of any function, which is typically called an observable, with the flow. So there are a lot of reference about this. It started with Koopman, and then more recently, it has a new birth in some sense since the beginning of 2000. And there are a few properties. Of course, it's a linear operator. It can be strongly continuous, provided that we choose the proper space like L2 or the space of continuous function on a compact set. There is an infinitesimal generator, which will be, in some sense, the derivative of the function f in the direction of the vector field. So this is for the properties. And as far as numerical methods will be considered, we will have to approximate this infinite dimensional operator into a finite dimensional subspace. So what we do in practice is to consider a set of basis functions that I denote by psi j. And this function will span a subspace Fn that we suppose that lie in the domain of the generator. And we will also have to choose a projection operator, which will project any function onto the subspace. And once we have these two ingredients, we can define compressions of the semigroup. So basically the projection of the semigroup, which is restricted to this subspace Fn. And we can do the same for the generator. And this compression, it's a finite rank operator. It can be represented by a matrix that I denote here by UT, which is an n by n matrix. And the nice thing is that we can typically obtain this matrix from data. So in practice, when we have data, the projection operator will be a discrete orthogonal projection, but we'll get the representation, one representation of a possible compression of the operator. And a well-known method to do so is the so-called extended dynamic mode decomposition, EDMD, and it was developed in 2015 by Williams and colleagues. And so the main point here is that we can compute this compression of the Koopman operators, this approximation from the data. Okay, so now let's talk about the identification problem itself. So just to set the problem, here we are given a bunch of data points. And in this case, we'll assume that we have pairs of data. So we have a data, which is a point in the state space, which is mapped to another point, yk, after some time ts, through the flow. Ts will be the sampling time. And so we have capital K pairs of such points. And from this, we would like to infer the vector field which has generated the flow phi t. And here we assume that we know that the vector field is expanded in some library function, in some basis function, which are denoted by gj here. And what we just want to find is the coefficients in front of this gj. So, for instance, we could assume that we know that it's a polynomial vector field, and we just want to find the different coefficients of the polynomial. But besides this, we also add some constraints. we want a linear method. So in some sense, we just want to use linear optimization, so least square optimization, least square problem. And the issue is that because it's a nonlinear dynamics, usually what we would need is a nonlinear method, so nonlinear identification. But there are other methods to do so. And for instance, you could try to estimate the time derivative from the data. And if you can estimate the time derivative, and you know that the vector field is of this form, then it's again a linear optimization to obtain the coefficient Cj. But here we do not allow ourselves to estimate derivatives, because we could assume that the sampling time is too large, which can happen, for instance, in biology, or also because data are too noisy. And so we know that it's not good to estimate directly derivatives and to perform the identification of derivative. So we need to find another way and still obtain a linear method. And so it's why we can obtain through this Koopmanism. So again, instead of going directly from the data points to the vector field, so through a direct method that would use the knowledge of the time derivative, we'll make some detour through the Koopman operator. So what we'll do first is to lift the data. So basically, it means that we'll evaluate the data points in the basis function. So we'll evaluate the value of the basis function at the data points. And once we have done this, we can use the EDMD algorithm, and we can obtain the compression of the operator through this matrix, which represents this compression. And then from this matrix, we can take the logarithm and divide by TS, the sampling time. And once we have this new operator that I define by, that I denote by AN, then we can recover the vector field, because we can show that this operator AN will converge strongly to the compression of the generator applied to F when the sampling time tends to 0. And recall that the generator is directly related to the vector field. So once we have the compression of the generator, in some sense we have some approximation of the generator, we have also some approximation of the vector field. Typically, we could simply apply the identity function, the generator to the identity function, and we recover the different components of the vector field. And so it's what we can do with this method. So we're lifting linear identification of the Koopman operator itself in some sense, and then lifting back to recover the vector field. So we have some convergence results. So I will not really enter into the details. You can check the paper if you are interested. But basically, what we can show is that if the basis functions contain the dictionary function, so recall that we assume that the vector field is expanded in some dictionary function Gj. So if we choose the right basis function, so the library function are in the basis function, then we can show that the coefficient, the estimated coefficient will tend to 0 when the sampling time tends to 0. So in fact, we'll use this property with the strong convergence of the operator AN through to LN. But we could also consider the case where we do not know a priori the right library function. So in this case, we would select functions psi_j, which are not the library function. And if we still consider the identity function in this function, we need some property, some regularity, so C1 function. And we need that the span of this basis function is dense in L2. Then we can show that the vector field that will estimate through this wrong basis function, this wrong library function, will still converge through to the right vector field in L2 now, provided not only that the sampling time tends to 0, but also that the number of basis function and the number of data tends to infinity. Okay, so I said that I would not really focus on numerical methods, so I have not given you the detail of the numerical methods, but what I can just show is that it works. So here are a few examples with different kinds of dynamics, with like limit cycle, unstable, chaotic, and so on. And in blue, we have the exact coefficient, and the red crosses are the estimated coefficient. And you can see that it works almost perfectly. Okay, so very briefly, there is also a dual method, because the main issue with the method is that we need to consider basis function, but it might be, we might have to consider too many basis functions when the dimension of the system is very high. For instance, if you have a 100 state and you need to consider all possible monomials up to some degree, it might really, the number might really blow up. And instead of this, we can consider a dual method, which is based on the fact that we'll try to identify the dual of the Koopman operator, so in the conjugate space of bounded linear functionals. So in this case, our subspace will be spanned by some evaluation functional at the sample point, and the compression of the operator will be represented by a matrix K by K, where K is the number of data. So now it doesn't depend on the number of Bayesian functions that we would like to consider. And in this case, we can also show that we have good convergence results. So in this case, the method will give us directly the value of the vector field at the different sample points. And from this value of the vector field at the sample points, we can again perform some regression and obtain the coefficient. And here is an example where we have almost 200,000 coefficients to estimate and only 1,000 data points. And maybe it's not clear, but it works quite well, actually. Okay, so finally, the last part of the talk, how can we apply this method to identify PDEs? So now we are given a nonlinear infinite dimensional system, so like in the previous talks by Henrik. And basically we assume that this infinite dimensional system is a PDE, where we have, which is described by a nonlinear operator, W, which is defined on some space U, which is a Hilbert space. And we assume that this PDE will generate a strongly continuous nonlinear flow that I denote again by phi. And the idea is again, by having some pairs of data, so pair UK and phi TS of UK, how can we obtain the PDE, where we again assume that our nonlinear operator W is expanded in some library operators WJ. And again, we have the same constraint as before. So first, we need to define the Koopman semigroup on this kind of for this kind of system. So this is very strongly related to Henrik's talk, but here we'll rather follow some more some less recent work. So mainly the work by Doro and Neuberger, and in the sense that we'll not, unfortunately, have the strong continuity property anymore, as Henrik explained. So we'll consider a space of continuous bounded functional. And the Koopman semigroup will be, again, the composition between this functional and the flow. Now, maybe to partially answer Rainer's question, so we do not have an infinitesimal generator, but we can still define a generator, which is the Lie generator. And it has the following form. It is basically the derivative of the functional in the direction of the vector field. So in this case, it can be interpreted and written in the sense of a Gatto derivative in the direction of WU. So it's really the equivalent of our gradient multiplied by the gradient of the function multiplied by the vector field. And again, we can define a compression of the operator of the semigroup and of this Lie generator. Okay, and now that we have this, we can still use the same trick. So with this Koopman operator, identify the Koopman operator in directly in this lifted space. Again, we can define this operator AN. But now there is a slight difference. It's that we do not have strong convergence, mainly because the semigroup is not strongly continuous anymore. So we have a weaker convergence, which is a pointwise convergence. So we need to evaluate the functional at some u, but still we have convergence when the time ts tends to 0. And again, once we have this, it means that we obtain the compression, so the approximation of the Lie derivative, the Lie generator, sorry, which means that we have directly the expression of this nonlinear operator W. So very quickly, we have again convergence results. So we can show that if we select the right basis function, we can have the convergence of the coefficient to 0 when Ts tends to 0. When I say that we should select the right basis function, it means that our basis function will be inner product between the dictionary operator WG we applied to the function, and inner product with some weight function W, which is in the space U. So we know a priori the WG. So if we have this, we show that the error on the coefficient tends to 0, and this pointwise conversion was sufficient to prove this convergence. Again, the details are in the archive paper, so I'm not entering into the details. And if we do not know a priori the WG, so we use basically other operator, V, Vj, and we reconstruct the operator of the PDE through this operator Vj, Vi here, then we can show that we have some, not a convergence, but we can show that the estimated operator will converge to an operator which will minimize some sort of least square error. So it's not a convergence to 0, so it's not as good as before where we had this strong continuity convergence property, but still it shows that it gives us some result which is not too bad in some sense. But there is definitely room for improvement in this case. Again, just to show you that it works, but it's just for illustrative purpose. So here we assume that the solution exists, that we choose proper space and so on. But we have applied the method on different kind of PDEs, and again, we can obtain good results. So I think that's it. So just to summarize, so we have seen that we can use this Koopmanism to apply on the problem of identification. So we have obtained two kind of dual lifting methods to identify ODEs. And we have a method which works also for PDEs. Maybe I would like just to spend 1 or 2 minutes on perspective. So as I said, there is definitely room for improvement of the PDE identification method, especially on the theoretical part and also in the numerical part, actually. And in particular, it would be very nice to use Henrik's result to recover properties of a strongly continuous semigroup and get a stronger convergent results for the method. Other general perspective, again, in the context of using this Koopmanism for infinite dimensional dynamical systems, I think a very important and very interesting topic would be stability of nonlinear PDEs, as Henrik mentioned. And in this case, spectral analysis would be could be really key, because we know that there are a direct connection, at least in the finite dimensional case, between the spectral analysis, spectral properties of the operator, and stability of attractors. And so it would be nice to have the same for infinite dimensional dynamical systems. Also, something which might be of great interest in the context, for instance, of control theory is to consider system with inputs. And if we want to consider in a very rigorous way and still get the semigroup property, in this case, we might need to consider the Koopman operator, which acts on some functions which are defined not only on the state space, but also on the space of inputs. And so even for finite dimensional dynamics, we would still have to consider, in some sense, a dynamical system in infinite dimension, because we also have to consider dynamics on the inputs themselves, and it's already in infinite dimension. And maybe it might be also be some room to apply Henrik results. So I think I have finished the talk, so I thank you for your attention.
Thank you, Alexandre, for this interesting perspective on Koopmanism from the applied side. So any questions or comments?
Yes,
Jochen, you?
I would have a question, yes. For your ODE system identification method, you mentioned there's a matrix logarithm at one point.
Yes.
So I think in general, a matrix has, of course, more than one logarithm. Is there a particular way how you define it, or which logarithm you use?
This is a very good question, and this is really the tricky point. So I use the principal branch of the logarithm, but we might have issues, for instance, if the sampling time is not large enough, because in this case, in fact, you have the eigenvalue will always be in some strip, and because of the sampling time, we might. It's difficult to explain like this, but we might need to select another branch of the logarithm, but it's difficult to know in advance. So this is really an issue. And it's why in practice, no, in theory, I mean, we need to consider that the sampling time tends to 0. But fortunately in practice, numerically, it can work even with somehow large sampling time. But you are right, and this is definitely the main issue of the method, I would say.
Thank you.
More questions?
Yes, I have a question. Thank you for the talk. Maybe I did not get it, but you said that if you do numerical differentiation, this might not be so robust with respect to noise.
Yes.
What about your approach? Is this more robust with respect to noise?
It's not that much robust to noise, I would say, but still, if you have some small level of noise, then it works better than just considering a very naive method for computing derivatives. So in the paper, the journal version paper, there are some tests on this where we can see that definitely the method works better than a naive method, but still it's not so robust to noise. So if noise is too large, but of course it's always like this, then the method does not work so well. And again, there is room for improvement, but definitely it works better than a naive method to compute derivative. In some sense, we could think of this method as a smart way to compute derivative, I would say, or a complicated way, a sophisticated way to compute derivatives.
And to put it into Koopman language, do you think it's the reason is that the semi-group is just strongly continuous and not uniformly continuous?
So it's not uniformly continuous, but I'm not sure I get your question.
I was just wondering, trying to follow the approach of formulating things in Koopman language. So I was wondering if this lack of control of noise is due to the property that the Koopman semi-group is only strongly continuous, but not.
I don't know. This is a good question. I do not have the answer like this. So you mean if it were uniformly continuous, it would be more robust to noise? Is it what you would suggest?
Yeah, this is what I was thinking. Maybe if this is the reason why robustness with respect to noise is not.
Yes, probably. I should think about this.
But uniformly continuous semigroups have bounded generators.
Yeah, right.
Okay. Yeah. I see the connection. Yeah.
Okay, but thank you.
You're welcome.
Okay. More questions? So if not, I thank all the speakers for this very interesting section. And I wish you a good but short but good lunch. And hopefully we'll see you again this afternoon.